Assalamualaikum warahmatullahi wabarakatuh, and a very good day to my beloved panels, Professor in Senior Dr. Hambali bin Arep, Alliance Ariff, Associate Professor Dr. Muhammad Shahir bin Kasim, and last but not least, Associate Professor Dr. Shajahan bin Maidin. My name is Ahmad Diaurrahman Bin Humaidi from the Faculty of Manufacturing Engineer, and today I'm about to explain my project, which is quality study of smart material polymeric filaments with shape memory effect for 4D printing application. And my supervisor for this project is Madam Ruzy Haryati binti Hambali. Before I proceed, let me explain why we were doing this project in the first place. This project integrated from collaboration, 3 collaborative partners, which are Dr. Nur Hafifi bin Hisham, Branch Manager, Physiotherapist at SOKSO Rehabilitation Center, Malaysia, and Associate Professor Dr. Haize Manaf, Clinical Rehabilitation and Exercise Research Group, UTeM. And my study focusing on quality study of smart material polymeric filaments with shape memory effect for 4D printing application to ensure the material and application suitability. In a nutshell, 4D printing refers to 3D printed objects that have the ability to reshape or self-assemble over time. It involves strategically positioning rigid and expandable materials next to each other within one 3D printed component. When the expandable materials come into contact with water, they grow up to 200% of their original volume, changing their shape and effectively repositioning the rigid materials on either side of them. Depending on the expandable material used, the contact substance necessary for it to change shape could be water, heat, light, temperature, even pH value, and another range of other simple energy input. The idea behind 4D printing is that we take multi-material 3D printing so we can deposit multiple materials and can add a new capability, which is transformation. That right off the bat, the parts can transform from one shape to another shape directly on their own. And this is like robotics without wires or motors. So we can completely print this part and it can transform into something else. To make it clearer, in infrastructure, let's just take one example. We take piping. In water pipes, we have fixed capacity water pipes that have fixed flow rates, except for expensive pumps and valves. We bury them in the ground. If anything changes, if the environment changes, the ground moves or demand changes, we have to start from scratch and take them out and replace them. But with 4D printing, we can combine the world of the nanoscale programmable adaptive materials and the built environment. It doesn't mean automated machines or smart machines that replace humans, but it is just programmable materials that build themselves, and that's called self-assembly, which is a process by which disordered parts build an ordered structure through only local interaction. 4D printing arises as new technology and has numerous potential that implements dynamic improvement in printed structures using smart materials. These dynamic scaffolds enable engineered tissue to undergo morphological pre-planned way. The layer-by-layer 4D printing construction process has a distinct feature that allows highly complex structure to be built quickly. This technique allows the fabrication of biological structures using tissue-like materials such as hydrogels to be applied for tissue regeneration. However, there is a gap that 4D printing needs to be focused on the success to fabricate the part. First, the how must ensure that the material used for 4D printing is able to react to its environment and changes over time and act as a programmable matter to its function. Moreover, limited access and consistent data are one part of the problem that needs to be faced as the 4D printing is about to develop. This project aims to study the thermal reaction and transformation of polymeric filaments of smart material with shape memory effect for 4D printing application to fabricate 4D smart material printed parts for human tissue replacement using 4D printing filaments, which is a composite of material. To determine the quality of mechanical properties for the printed parts include the tensile test, dimensional accuracy, and thermal testing. The scope is to apply additive manufacturing technology and 4D printing parts using fused deposition modeling on fabricating the test specimen. SolidWorks 3D modeling and simulation software is used to propose modeling design and simulation. Examine and analyze the transformation of the smart material response of the printed specimen by exposing it on the thermal condition. Determine the quality of the 4D specimens. Focus on the strength of the printed parts by using ultimate tensile machine. Follow standard ASTM D628. Compare the final product quality printed by using smart material polymeric filament with 3D printed filament PLA. For the literature review, additive manufacturing has created an impact in all industry sectors, including aerospace, construction, medical, and military. Provides flexibility in design, significant material saving, as well as customization and individualism. For smart material, Bajpai stated, instead of the substance itself, one dominant viewpoint is to rely on the reaction or operation of the outcome. Self-sensing, self-acting, self-diagnosing, self-healing, and shape change can result from expected responses. Intelligent or stimulus-responsive materials are capable of reacting to heat, chemicals, and light. Now, we come to the methodology. Here is the process flowchart. We start with the identification of studies background, problem statement, objective, scope, and research significance, followed by a literature review of 4D printing, smart material, and response. Next, we determine the research and analysis of the suitable method. Once done with it, we define the type of material, parameter, and method of experiment. Design the 4D part using SolidWorks software and fabricate by using the FDM. Inspection once done, fabricating is a must, following with testing. If it is accepted, then dimensional accuracy and tensile tests will take their part and lead to the thermal testing, analysis data, and report. If it's not, then it will go back to define the type of material, parameter, and method of experiment. Fused deposition modeling is one of the most common 3D printing techniques available. FDM is a form of 3D printing technology that falls under the general process of material extrusion. This type of process uses a thermoplastic material that is heated to a moldable state and then deposited onto a build plate or printer bed in the layer-by-layer process. During the fabrication process, the position of the nozzle is controlled by a computer program and moved in an XY plane in order to create the desired pattern. Once layer is completed, the nozzle moves upwards along the Z-axis, a predefined distance to print the next layer. This process continues until the desired form is created. So here is the table of 4D printing of polymers for tissue engineering applications. All of the applications use the FDM as their printing method for tissue engineering applications. Just as information, MSC or mesenchymal stem cells are adult stem cells isolated from different sources that can differentiate into other types of cells. In humans, these sources include muscle, fat, bone, ligament, and other connective tissue. To achieve the aim of this project, from the previous objective is to study thermal reaction and transformation of polymeric filaments of smart material with shape memory effect for 4D printing application. And the tool of this objective are doing the research on the behavior of SMP with the stimulus, scope on temperature stimuli on the SME. Second one is to fabricate for the smart material printed parts for human tissue replacement. So we need to design the part for the printing part and fabricating by using fused deposition modeling. Last one is to determine the quality of mechanical properties for the printed parts, include the tensile test, dimensional accuracy, and thermal testing. This objective can be achieved by using the tensile test ASTM D638, dimensional accuracy, thermal testing, and record the data and compare between 4D and 3D materials. Here comes the last part, which is the expected result. The expected result for this project are to obtain the tissue replacement for the human body part using 4D printing, identifying the result of mechanical properties for tensile test of printed part, identifying result for internal behavior of the specimen smart material, the comparison of the printing quality of the printed part by using two different material, PLA and smart material. I think that is all for me. Thank you to all panels. Professor Insinyur Dr. Hambali bin Arep Alliance Ariff, Associate Professor Dr. Muhammad Shahir bin Kasim, and Associate Professor Dr. Shajahan bin Maidin for lending me your time and ears. And I will end this presentation here. For any question and inquiries, can contact me at any of my social platforms. Thank you and Assalamualaikum.